So in our third lesson, we're going to look at some vectors in mechanics, and we're going to draw together all of our knowledge of position vectors, of magnitude of vectors, of distance between vectors, and we're going to put all that together into a mechanics context where we're going to be talking about vectors for velocity and position into one question. So we have this situation where we have at 6 a.m. we've got boat A and boat B. Boat A has a position vector of 12I minus 11j kilometers, and it moves with a constant velocity 9I minus 6j kilometers per hour. So that means that boat A over here, if we were to imagine it on a set of coordinate axes, which is a good way to kind of visualize these vectors if you're unsure, boat A starts off down here somewhere. So from our origin O, 12 to the right and 11 down. That's where boat A starts from this vector. And then it moves, and its constant velocity here tells us the direction it's going to move. So it goes from there, it goes 9 to the right and 6 down every hour. All right, so we need to know the number of hours in order to figure out exactly where this boat is, but that means we can just put this information together. So for boat A, I'm going to say that it begins its journey at 12 minus 11. We know that it moves on the course 9 minus 6. Now, how far along this 9 minus 6 it travels is entirely dependent on the number of hours. Every hour it moves 9 along, 6 down, 9 along, 6 down. So we need to multiply that vector by t, which is the number of hours it moves. We can simplify this into a single vector by combining the I components, 12 plus t times 9. And we've got minus 11 minus 6t, so minus 11 plus t times minus 6. And that means that our position vector of A, we need to write it in terms of I and j simply because the question is written in i's and j's. It doesn't specify, but we should if the question has i's and j's in it. And we're going to say it's plus 9 minus 6t, 11 minus 6t lots of j. So that's our position vector of A. For B, we're going to do exactly the same thing. We're going to write its starting point, which is 40 minus 39. And then we're going to multiply its velocity vector by t, which is minus 12 and 15. We'll combine those two into a single column vector. So we have 40 minus 12t, and then we have minus 39 plus 15t. So our position vector of B in terms of i's and j's is 40 minus 12t I plus minus 39 plus 15t. So those are our position vectors for A and B. And just to quickly recap, it's about the starting point plus the direction that it moves multiplied by the number of hours that it moves for. All right. So for part B, we're asked, it says, show that if A and B continue their current course and speed, that they will collide, and find the time and position vector at which this occurs. Now you can see from my diagram, although crudely drawn, it's entirely possible that these two boats will collide, and we're being asked to find out if they do, and if they do, where are they when they collide. So the way that we do this is to look at our two position vectors and think, well, if they collide, they have to be in exactly the same position at the same time. So the I components of each of A and B must be the same. Also the J components. So we can use that, and we can say that the 12 plus 9t then must be equal to the 40 minus 12t. All right, for them to be in the same position horizontally, those two must be the same. So we can go and work that out, and we end up with 21t equals 28. Okay, so this gives us that t is 4/3. Now that tells us they're in the same position horizontally. For them to be in the same position vertically, we need the minus 11 minus 6t and the minus 39 plus 15t to be equal to one another. So we'll solve this equation in exactly the same way, and we get that t again is 4/3, which is good. That means that they are both in the same position at the same time. Now we need to write the time that they are colliding. So 4/3 is 1 1/3, which is 1 hour and 20 minutes because it's t hours. And then that means they collide at 7:20 a.m. because t in the question is given as the time after 6 a.m. So where is the position? Where are they when they collide? Well, in order to find out where they are, we just take our t value, 4/3, and we substitute into either one of these two vectors. So if I substitute into A, we'll have 12 plus 9 times 4/3, and that's our I component. And then we've got minus 11 minus 6 times 4/3 is our J component. So we're going to have 12 plus 12, 9 times 4/3 is 12, so we've got 24I. And then 6 times 4/3, which is 8, minus 11 minus 8 is minus 19J. So I should write, instead of plus, we've got minus 19J. So there is the time, 7:20 a.m., and there is the position that they are, 24I minus 19J. So in part C, our question becomes a little bit more complicated, only a little bit more complicated, because it says at 7 a.m., boat A realizes that a collision is imminent. And then it changes course, so its velocity is now minus 18 plus 21, and that means its direction has changed, so that it's trying to avoid the collision. So in order to set this up, we need to know where is boat A when it realizes that there is a collision. Now, it was at 1 hour after it set off, so we can use t equals 1, so 7 a.m., 1 hour after 6 a.m. So we'll substitute t equals 1 into our A vector this time, and we'll work out where boat A is when it realized it was going to collide. So 12 plus 9 there, we've got 21, and minus 11 minus 6, we've got minus 17. So you can see that boat A was at 21 minus 17J when it knew that they was going to collide. Now that means we need to set up a new equation for A. Now that new equation for A is given by the position vector of where it was, 21 minus 17, when it realized it was going to collide, and then its new velocity, the new course it's plotting, so minus 18, 21, and that's going to be multiplied by the number of hours that it's traveling on its new course. All right? So this is the new equation for A after 7 a.m. So then we're asked, find the distance between the two ships at the time they would have collided. So then we need to work out, at 7:20 a.m., where is A? Well, A is going to be 21 minus 17 plus 1/3 of minus 18, 21. Now, the reason it's 1/3 is because this equation, 21 minus 17 minus 18, 21, that's its position at 7 a.m. At 7:20, it's 1/3 of an hour forward on its new velocity. So A then is going to be at 21 plus 1/3 of minus 18, which is 21 minus 6, which is 15, minus 17 plus 1/3 of 21, which is minus 10, which is minus 17 plus 7. And so that's where A is. Now we go back to part A of the question, or part B of the question, I should say, which is where is boat B? Well, boat B is at the initial point that we said that they were going to collide, 24 minus 19. Okay, because B didn't change course, so it's still going to be here. A changed course at 7 a.m., which was 1 hour after the 6 a.m., so we had a new equation, and we used the new equation to say it's 1/3 of an hour this time, so 20 minutes after the 7 a.m. to work out where it is. So now we're just being asked to work out the distance between the two. So we're going to be working at the vector AB, and we know from our calculations so far that AB is just OB minus OA, which is 24 and minus 19 minus 15 and minus 10, which is 24 minus 15, pardon me, gives us 9, and minus 19 minus minus 10 gives us minus 9. So that's the distance between A, B. We're being asked how far apart are the ships. We need the magnitude of that vector And so we do the square root of 9 squared plus minus 9 squared, which is using Pythagoras theorem again to find the distance between 2 points. So we've got square root of 162, which then if we simplify, pardon me while I get my calculator and cheat and not simplify this in my head, square root of 162, so 9 root 2 kilometers. And that's it. We are done. And that's as complicated as the vectors questions are going to get for you. So just a quick recap. The first part, we wrote down equations for where A is going to be at a set hour after 6 a.m. and also for B. That allowed us to make those two equations equal to work out where and when they were going to collide. Then we had this additional information where A changed course 1 hour after it set off. So we worked out where it was when it realized it needed to change course. Then it had a new velocity that it was traveling on. The question asked us, at the time of the initial collision, where would A be now, effectively? So at 7:20 a.m., we had to substitute 1/3 into this position vector. And the reason it's 1/3 this time is because this is its position at 7 a.m. At 7:20 a.m., it's 1/3 of an hour forward. So we got the new position of A. Position of B was where it would have collided initially. To find the distance between these two, we need the vector that joins A and B. So we work that out. And then to find the distance of that vector, we use Pythagoras theorem. Okay, thank you very much for listening. See you later.